Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on X-ray on techniques of materials characterization, and we are discussing about X-ray diffraction. This is module 12, that is, this is the last module of this course, and in this lecture we will be discussing, we will continue the discussion about intensity of diffracted beam, and we will try to start discussion about X-ray diffraction from a real specimen, and how to analyze that, how to get information out of the regular X-ray and X-ray pattern which you normally use to see XRD profile. So, how to analyze that profile and how does it looks like, all of this we will be discussing in this module basically. So, from the last module we were discussing about the intensity of diffracted beam, and we have discussed about the structure factor and various other factors. We discussed about the multiplicity factor, and we started discussing about temperature factor. So, we will be continuing with the temperature factor now, and we will discuss about another factor, that is called absorption factor. After finishing these two, we will try to address this question of diffraction from a real specimen. Okay. So, temperature factor, if you remember, we discussed that temperature, basically this factor comes because of thermal vibration of the atoms that causes the change in the d value, which is again seen in the shift of the peaks in the sin 2 theta axis. The peak is shifted, that is one. The expansion of the unit cell is one reason for this thermal vibration, or one of the effect of this thermal vibration, that is one. And then we have seen how this thermal vibration is basically causing the decrease in intensity of the diffracted beam with temperature increase, because the constructive interference that happens from planes from parallel or from parallel atomic planes, when an incident X-ray beam falls on these planes and Bragg's angle Bragg's condition is satisfied, then a constructive interference is expected, but that constructive interference doesn't peak, or it doesn't happen in the perfect way, or there is an imperfection in the constructive interference, or in the partial interference happens just because of this thermal vibration, which we discussed in that. And also we understood that the thermal vibration, and that basically this imperfection brings down the intensity of the diffracted beam overall, and this decrease is more seen at 2 theta, higher 2 theta angles, because there it involved with low d value, low interplanar spacing planes. So, these were what we discussed in the last class, and what now we will be discussing couple of other factors or couple of other characteristics of this temperature factor or temperature effect. So, first of all, the thermal vibration, as we just now we discussed that the thermal vibration basically changes the 2D. In a unit cell, it basically changes the interplanar spacing just because of this atomic vibration. The unit cell expands. So, as an effect to that, what will happen is basically the peak can shift in 2 theta, in the 2 theta axis, the peaks can shift. And this basically, as we will be understanding when we discuss about the diffraction of real specimens, we will understand that this change in 2 theta means the peak width basically should increase in the process, in the overall process. The peak width should increase, because if you imagine the temperature is not an uniform temperature increase, then at different places in the specimen, at different places, different unit cell will have different 2D values, different lattice parameter, or different unit cell will expand differently, that will cause different value for 2D. And that means for a particular plane, the D spacing will be different in different places. All of them, if now gives rise to the diffraction condition, if they satisfy at different sin 2 theta value, different sin 2 theta values, and that will ultimately will be seen in the broadening of the peak. That is what we call So, this is basically one of the effect, but what happens is in thermal vibration, this thermal vibration of the atoms around their mean position, this causes a very slight increase in the breadth of the XRD peak, which is measured at half maximum intensity, also known as FWHM, which we will discuss in this class if possible. So, this increase in the breadth of the XRD peak is very less. So, that means the this peak shifting or peak broadening effect that we discuss because of the unit cell expansion and all is very minute effect, or this thermal effect in increasing the peak width is a very minute effect. So, mostly the way thermal vibration affects the intensity or diffracted beam intensity is basically they reduces this diffracted beam intensity, but they did not cause much of a broadening of the peaks. So, diffraction lines all the way, if we go to up to the melting point, the diffraction lines remains quite sharp as they used to be at room temperature for most of the materials. So, that is a good news, that otherwise that effect will be very difficult to sort of characterize, or that effect, the big broadening effect will be very difficult to measure just because of the thermal vibration. So, you can see this is one such experiment done on titanium alloys, or two different titanium alloys. And here you can see at room temperature, this is one. So, this is a phase transformation. This is a classic case of phase transformation, which I was discussing in the last module, gamma to alpha. If you remember how the austenite and ferrite phase transformation happens and how different peaks evolve, from which we can identify this transformation. So, here also you can see that same thing, that as we increase the temperature, we are getting a completely different peak altogether, that is coming out at a certain temperature 1000 degree onward, completely peak, which is not there in this low temperature X-ray diffraction profile. Basically, alpha titanium is hexagonal, whereas beta titanium is body centered cubic. So, that peak appears only at high temperature, and from there we can find out temperature, this transformation temperature, we can find out which alpha, how they are related, these two phase, how they are related, and lots of other things we can identify. But the important point is, if we look at any of this peaks, the alpha peaks, let's imagine we are just interested in any of this alpha peaks, we can see that intensity is basically going down. If we imagine from here at room temperature all the way up to 1000 degree, the intensity of the alpha peak is slowly going down, but the width of the alpha peak does not really change that much. So, that is what I was meaning, that intensity, mostly thermal vibration, affects in the overall intensity of the peaks rather than changing the peak position as such. Okay, that is first thing. The second thing is that this mean amplitude of atomic vibration, this is not only a function of temperature, but also a function of the bonding characteristics of the material, which is reflected in terms of elastic stiffness or elastic constant of the material. So, we know that elastic constant is basically intrinsic property, and intrinsic property means it only depends on the bonding characteristics or the interatomic distance between the two atoms. So, that detects the elastic constant. So, that means the mean amplitude, this atomic vibration is also an intrinsic, it is a result of this intrinsic properties, or it is a result, it is manifested by through this intrinsic properties. It is related to the bonding characteristics of the materials, it is not only the temperature alone. So, what it does means is that at any given temperature, if the bonding is stronger, if the material is stiff, if the crystal is stiff, then this vibration amplitude will be lesser. That means if the bonding is less, then the atomic vibration, the amplitude of this atomic vibration will also be higher. If the less stiff materials, for example, if we go something like lead, which is very low atomic number and eventually very the bond strength is much lower to compare to something like a heavy higher number of high atomic number element like tungsten, where it is much higher, it is having an elastic constant which is much higher than something like a lead at least. So, if we compare these two different materials altogether, lead and versus tungsten, then this temperature effect, or rather first we start with the atomic vibration. So, the atomic vibration for lead, the amount of this average displacement about the mean position, this will be much higher for lead. That means the U, which we discussed in the last class, that U value will be much higher for lead as compared to the tungsten. So, again the peak, the decrease in intensity with the temperature, that will be much more prominent for something like lead as compared to tungsten. So, if the material is stiff, if the bonding is much stronger, then this atomic average displacement, atomic vibration will be less. Correspondingly, the decrease in intensity due to the increase in temperature will also be less. That means, in case of the, if you increase the atomic number, if the bonding is very stronger, that will increase this, or that will help to keep or to retain the intensity of the diffracted beam. Okay. So, other way around, we can say that substances which has low melting points, and low melting points of course is because they have low strength of the bonds are very low. So, low melting point substances will have large U value even at higher temperature. You can see this value for lead is given here at 220 degrees centigrade, which is very close to the room temperature. This reduces the intensity of the 2 theta diffraction line at a very high 2 theta, of course very high 2 theta. We already discussed that this temperature effect is more prominent for higher 2 theta peaks. So, there this intensity is only at 20 degrees centigrade, room temperature intensity is only 18% of the value of atoms at rest, which is absolute 0 temperature, close to theoretical value, but almost it has decreased almost like 82% from that value. So, that kind of a decrease we can expect with this. So, here also you can see that if you increase the temperature, the intensity drastically decreases compared to something like at close to room temperature or at lower temperature. So, that is important point to remember is that not only the temperature, but also the characteristic, bonding strength, all of these things is important when we calculate or when we consider the temperature effect on the diffracted intensity of X-ray beam. Okay. So, now there is another effect of this temperature effect called the temperature diffuse scattering. So, what happens is, besides the decrease in the overall intensity of the peak, the thermal vibration also causes something like increase in the background scattering. It causes a general coherent scattering which goes into the background, in making the background of the of this intensity. This does not take part in the diffraction phenomena. So, diffraction, this thermal diffuse scattering is nothing to do with the diffraction phenomena, constructive interference. So, that anyway is there, and temperature, increasing temperature is anyway affecting that constructive interference. Other than that, it produces some other coherent scattering effects in all possible direction, which is basically increases the diffraction, or basically increases the background for all possible 2 theta values at all possible direction, at all possible 2 theta values. It has nothing to do with the Bragg's condition, satisfaction of the Bragg's condition. This background pattern also increases with 2 theta values. So, as such, the intensity of the peaks decreases with higher 2 theta values, plus this temperature diffuse scattering, that intensity also increases with the 2 theta values. So, overall what happens is that at higher 2 theta values, because of the thermal vibration, two things happen at very high 2 theta values. Number one, the intensity of the beam or intensity of the diffracted beam anyway will decrease, plus the background also increases because of this temperature diffuse scattering. And at certain ultimate cases very close to the back reflection like 160 or 170 degree, if those conditions, it is very difficult to identify the peak from the background itself because of these two effects. Intensity of the diffracted beam decreases, plus the background intensity also increases, these two effects. So, if we see here that these are the 3 peaks, if these are the 3 peaks which are of the same intensity due to, if we ignore the thermal vibration effect or this temperature effect, if we ignore, if they have the same intensity, high angle peaks, of course very high angle peaks, if they have same intensity, if we keep the temperature factor aside, then they will have this kind of a temperature, this kind of an intensity profile because of two effects. One, their intensity will decrease. If you see here, the intensity is constantly decreased due to the temperature, the thermal vibration effect. Temperature continuously decreases due to thermal vibration effect at higher and higher 2 theta value, plus this background continuously increases with 2 theta value. So, both of them ultimately is affecting the absolute intensity of this peaks at higher 2 theta values. So, this is basically the effect, another effect of temperature, and why this is happening is basically the scattering at non-Bragg's angle is happening. This temperature diffusion scattering, as I just explained, the temperature diffuse scattering happens at non-Bragg's angle, and because of the displacement of atoms from their mean position, and this is somewhere similar to a crystal imperfection, which we will be discussing in this module. In the next few lectures we will be discussing. So, this basically causes a X-ray scattering at non-Bragg's angle, and that will be sort of, in some sense, that destroys the condition necessary for perfect destructive interference between rays other than non-Bragg. So, if you understand that constructive interference is completely, it is related to the Bragg's condition, satisfaction of the Bragg's condition. Other than those Bragg's condition, other than those sin theta value, ideally we should have a complete destructive interference. But because of this temperature diffuse scattering, we get some intensity for those non-Bragg angle diffraction, non-Bragg angle values. There also we will get some limited intensity of the X-ray beam. Not everything will undergo destructive interference. The perfect destructive interference will also be. So, temperature effect basically, number one, not only it will take that perfect constructive interference it will affect, but also it will affect the perfect destructive interference. So, one of this effect, imperfection in the constructive interference, it will decrease the intensity of the peak, and imperfections from perfect destructive interference will increase the background intensity. So, ultimately this is how the temperature will affect for both of them, and that will be reflected in the overall intensity of the diffracted beam. Okay. So, with this we are coming to the last factor that we will be discussing about the intensity of the diffracted beam, and that is the absorption factor. So, absorption factor is basically related to absorption, as the name suggests, it is related to X-ray absorption, and X-ray absorption we have already discussed in the first few lectures on X-ray. There we discussed how the absorption happened, true absorption and all of this. So, we are not going into that, but what happens is that the diffracted beam is of lower intensity than what we would expect if a specimen exists without any absorption. So, if the absorption is not there within the specimen, then the diffracted intensity will not decrease because of this factor. But since limited amount, some amount of absorption will always happen in the before the incident X-ray beam hitting the specimen and the diffracted beam reaching the detector. In the entire process, there will be some amount of absorption, X-ray absorption, that will definitely happen, and that will decrease the intensity of the diffracted beam even further. So, the way this one is included in the calculation of diffracted beam intensity, we call it absorption factor, and this absorption factor is expressed in terms of A theta. This is a number by which the calculated intensity is ultimately to be multiplied. So, this is very similar to the temperature factor. We will discuss how these two are related, absorption factor and temperature factor, but basically multiplicity factor, temperature factor, absorption factor, all of this ultimately gives me a number through which the diffracted intensity should be multiplied. Okay. And to take care of individual all of these effects. Now, the calculation of the this absorption factor, this related to the geometry of the diffraction method involved. We are not going into geometry of the diffraction, we vaguely saying we can have various type of geometries. For example, Laue diffraction method, Debye-Scherrer diffraction method, powder diffraction method, various type of diffraction experiments are there, where the geometry, ultimately it is all about the Bragg's condition satisfaction and all. The geometry of the diffraction means the X-ray source, the relative position of X-ray source, specimen and the detector. So, this and what type of detector we use, what type of source we use, based on those, this X-ray diffraction geometry will vary. We are not going into that, but this absorption factor, for all other factors this does not matter much, but for absorption factor this really depends on what type of geometry we are using. For example, if we use, or if we think of something like Debye-Scherrer method, which we are not discussing, but if you are interested you can go through the book, reference book, and can read about it, what is Debye-Scherrer method. So, in Debye-Scherrer method what happens is that we use the specimen in the form of a cylinder, basically something like this. So, here from this cylindrical specimen what we can understand is that absorption increases as theta decreases. As the angle of scattering decreases, the absorption increases for this kind of a cylindrical specimen. Now, why is it so? This is because if we understand or if we see this kind of a material, this cylindrical material. So, the beam is entering here, the incident beam is entering here, and then it is getting diffracted for different scattering angle, different 2 theta values, it is getting diffracted. Now, for different type of 2 theta values, the incident ray and the diffracted ray, the amount of or the path they have to travel within the specimen, that varies depending on theta. So, if we imagine something like a low 2 theta, almost like a forward scattering, low 2 theta diffraction. In that case, this incident beam, the incident beam and the diffracted beam, they have to spend more, or they have to cover, or they have to travel and more path or more amount of path within this specimen itself. So, that means they will be having more chances to get absorbed by the specimen here itself. Compared to that, if we consider low 2 theta value, low 2 theta diffraction or low 2 theta scattering, almost close to the back scattering here. Other way around. If we consider something like high 2 theta, so this is a back scattering here. If we consider something like a high 2 theta value here, for high 2 theta value, this incident X-ray and the diffracted X-ray both will be spending a much little path within this specimen here, compared to something like a forward scattering. There in a low 2 theta value, low 2 theta scattering, this has to spend or this has to undergo a larger path here. Here the path is A, B, C for low 2 theta scattering, and here the path is D, E, F. This much is a D, E plus E, F. This is the path. So, this path is much lower than this A, B plus B, C path, of course. So, that means here itself we can understand that the amount of absorption, the chances of this incident X-ray and diffracted X-ray to get absorbed within the specimen, this has a relationship with the angle of scattering. For forward scattering, which is lower 2 theta value, this absorption will be higher, and for backward scattering close to higher, very high 2 theta value, this chances of absorption will be much lower. And this will of course depend on the linear absorption coefficient of the material. So, if we imagine something like a highly absorptive specimen, something like a tungsten, so there this entire diffraction phenomena or entire absorption, the entire diffraction is basically will happen for this very small region within close to the surface. All other beams which are entering in the specimen, they will be all absorbed, there will be nothing left for diffraction itself. So, the entire diffraction phenomena will happen from a region very close to the surface. There also what we can understand that the forward scattering, so forward scattering means it has to come all the way here and then get scattered. So, the amount of forward scattered beam, the intensity of the forward scattered beam will be much lower compared to the intensity of the back scattered beam, which is means at high 2 theta values. So, forward scattering is basically limited here very close to the surface. These two extreme cases, somewhere within this the forward scattering condition is not at all valid. Okay. So, overall what we understand, the same thing is written, the back scattered high 2 theta scattering and high 2 theta angles peaks, the scattering, the absorption factor is much lower compared to low 2 theta values. So, this difference in high and low 2 theta reflection of course decreases as the linear absorption coefficient decreases. So, if we imagine something lighter element which is which does not have much of a linear absorption coefficient, true absorption is lower and so on and so forth. So, with a decrease in linear absorption coefficient, this overall absorption factor will decrease, and then the difference in absorption between a high 2 theta peak and a low 2 theta peak will also be decreasing, but it will be still there. So, it depends not only on the angle, the 2 theta angle, it also depends on the linear absorption coefficient. For linear absorption, just like temperature factor, not only it depends on temperature itself, it also depends on the 2 theta. Here not only the 2 theta value, it will also depend on this linear absorption coefficient. If the linear absorption coefficient is lower, lesser absorption overall, then the difference between low 2 theta and high theta values those peaks will also be lower. If the linear absorption coefficient is very high, something like a tungsten, then there will be a considerable difference between the intensity of 2 theta, low 2 theta and high 2 theta peaks due to the absorption factor. Okay. Now, this is Debye-Sharron method, but more than Debye-Sharron method, we should discuss about powder diffraction method, that is what we normally use. So, in powder diffraction method, we normally consider these powders like a flat plate. So, it is kept, the powders are kept like a flat plate, or normally it is kept in a groove on a plate, in a groove we put the powder. So, we can imagine this as a flat plate, which is making an equal angle with the incident and diffracted beam, and that angle is basically the theta angle. So, this here what happens is that the absorption factor A theta, this is equal to 1 by 2 mu. That means, this absorption factor is independent of the theta value in case of a powder diffraction specimen. In case of a Debye-Sharron method, it is obviously decreases or obviously depends on the absorption factor depends on both the linear absorption coefficient as well as the 2 theta. Here for powder diffraction method, this fortunately does not depend on the theta value. So, it only depends on the linear absorption coefficient. So, the absorption, the amount of absorption is exactly the same for low 2 theta for back reflection condition, or sorry, forward reflection condition, low 2 theta peak and high 2 theta peak, which is back reflection condition. It only depends on the linear absorption coefficient of the material that is used there. Now, why is it so? What happens is, for a flat plate like this, if we imagine, first let us imagine a low 2 theta condition. So, this beam is falling somewhere over here. What it will does is, this beam will, the amount of area this beam is saying, the cross section, basically the beam for a fixed size of the beam. If the beam size is the fixed, then the incident beam, the fixed, the depth of this X-ray penetration, this will be small. That means, if the angle of incident is shallow, then the depth of penetration will also be small for a fixed cross section of the beam. Then exactly reverse will happen if theta is large. If the angle of incident is large here, then the depth of penetration will also be larger. Effectively, what will happen is that the effective irradiated volume, this cross section. So, in a shallow angle, the cross section will increase, the cross section over which this beam cross section will increase, but the depth of penetration will be small. If the beam is falling at a higher angle, then this cross section, this irradiated area, this area will be small, but the penetration depth will be large. Altogether, the irradiated volume will remain constant for all d theta value. It will be independent of the 2 theta. In case of Debye-Sharron, this is what was changing. The irradiated volume was changing. If you see this this here, the irradiated volume was changing for forward reflection versus backward reflection. Here for powder diffraction, this irradiated volume remains constant for any kind of theta values. So, this ultimately the absorption factor becomes independent of theta and only depends on the linear absorption coefficient of the material. That is it, all other conditions being the same, remains the same. So, that means finally the absorption factor, this basically decreases all the diffracted beam, intensity of all diffracted beams will decrease by the same factor, and it does not finally enter into the calculations of relative intensity. So, in case of a powder specimen, we can safely remove the absorption factor when we calculate the final diffracted intensity at all. Okay. Now, let us see the relationship between the temperature and absorption factor. So, temperature factor E raised to the power 2m and absorption factor, which is A theta. In case of a cylindrical specimen, that means in case of Debye-Sharron method, this will depend on the diffraction angle in opposite way, if you remember. So, this is the temperature factor. Temperature factor decreases with diffraction angle. So, the temperature factor decreases with diffraction angle and diffracted intensity decreases as the 2 theta value is increasing. For high 2 theta peaks, temperature factor will decrease the intensity. On the other hand side, the absorption factor increases the diffracted beam intensity, or it is more effective on the lower 2 theta beams rather than the higher 2 theta diffracted beams. So, absorption factor will cause more intensity decrease for low 2 theta diffraction beam compared to the high 2 theta diffraction beam. So, in that what it does mean is that the temperature factor and absorption factor goes in two opposite directions. They have opposite relationship with the 2 theta beam. In high 2 theta, the intensity of the diffracted beam will decrease very little by absorption, but much higher by thermal agitation, while in low 2 theta, the diffracted beam intensity will be mostly decreased by absorption effect, but not so much by the temperature effect. So, these two effects we can safely say for cylindrical specimen as such, these two effects basically cancels each other. May not be exactly cancelling each other, but they are sort of cancelled each other. Only for powder specimen, anyway the diffraction factor is, the absorption factor is independent of theta. So, their entire decrease in diffracted intensity with 2 theta is because of the temperature factor. So, for powder specimen, temperature factor will be there, absorption factor will not be there, and for a spherical, the cylindrical specimen, Debye-Scherrer method, the temperature factor and absorption factor will be cancelling each other basically. So, finally, in the calculation of diffracted intensity, both of these factors will not come, because, and this is a very fortunate situation, because the exact calculation of whether either the temperature factor or absorption factor is quite difficult for any kind of a material. Okay. So, for a Debye-Scherrer method, we do not need to consider temperature factor or absorption factor separately. They can be cancelling each other, and neither of them will enter in the final diffracted beam intensity. And for powder specimen, anyway we have to consider the temperature factor, because absorption factor is 0 or absorption factor is not there for this powdered specimen. So, we will be stopping here, and in the next lecture we will be discussing about the diffraction intensity or this X-ray diffraction profile of a real specimen and how to analyze that. So, goodbye.